Hello, this is Semin Kim. I'm going to explain quantum computers. There is a speed that's fundamentally impossible to overcome with a conventional computer. Therefore, supercomputer was developed. However, with the advent of quantum computers based on quantum mechanics in modern times, the amount of information that can be processed at once has increased. You may have heard that quantum computers are faster than conventional computers. A classical computer performs operations using classical bits, which can be either 0 or 1. Now in contrast, a quantum computer uses quantum bits or qubits. A quantum bit has a more fluid, non-binary identity. It can exist in a superposition or a combination of 0 and 1. And it gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit, a single photon, a nucleus, or an electron. How does superposition of information have to do with speed? Let's take an example. I want to go Hanwha Eagles Park for see baseball from my dormitory, and assume that there are 20 routes to arrive Hanwha Eagles Park. To find the fastest way to baseball park, I have to calculate the time it takes for each route. In order to find the fastest route, I must calculate 20 routes one by one. After all calculations are completed, each result stored in the bit must be compared. Only then can figure out the fastest way. This is the way it works on conventional computers. This time, we use a quantum computer. Because the information is superpositioned, there are 20 passes are also overlapped. Therefore, 20 states start at the same time. And the moment the route the destination is first observed, the result is saved at qubit. It's done with one calculation. Quantum computers use two properties of quantum mechanics. These are quantum superposition and quantum entanglement. Quantum superposition is that an electron maintains the randomness of its spin direction until the quantum is measured, and quantum entanglement is that when one of the entangled quantum is observed, the remaining quantum are also fixed regardless of distance. As I mentioned before, quantum computers operating using combinations of quantum states called qubits. In existing computers, the state of the bit, which is basic unit of information, is 0 or 1. The qubit, the unit of information in quantum computers, can have two states at the same time, 0 and 1. This is because quantum computers operate in a state that cannot be determined whether it is 0 or 1. Thus, two qubits have four states, 0, 0, 0, 1, 1, 0, 1, 1 at the same time. 8 states when 3 qubits are entangled, and 16 states when 4 qubits are entangled. In other words, the computational speed of a quantum computer increased by 2 power n times per qubit, count through parallel processing. If 10 qubits, then 1024 pieces of information are contained, compared to combinational computers, which are only 10 bits of information. It can process more than 100 times the amount of information at once. However, just because the number of operations is low and a large amount of information can be processed at once is not necessarily fast. Rather, if the time it takes to perform an operation once is very long, it will be useless than a conventional computer. Also, manipulating qubits requires precise control at the level of invisible particles and require very low temperature. In addition, the qubits fit each other well for a certain period of time, so they must all be entangled in an overlapping state. But when the number of qubits increases or the temperature rises, interactions with the surrounding occur, causing them to shift and collapse. The state that quantum computers have proven to outperform conventional computers is called quantum supremacy. At least 50 qubits are required to achieve this, But in reality, even keeping a few qubits coherent is not an easy task. It is not enough for quantum computers to be commercialized yet, but it is the first experimental evidence that it is possible to use the principles of quantum mechanics in the real world. Thank you for listening.